Hello again, everyone. This is me, Assam Hilmi, and I will be your moderator on today's webinar. I'm a success partner with OBA Energy. Before going to our presentation today, I'd like to make sure that my voice is clear. So if someone would volunteer to confirm this in the chat area, please type 1 or something. Please confirm that you are listening to me and that you see my screen clear. Yeah, thank you, Muhammad. Thank you so much. So for today's webinar, we have a very special webinar on the title Pipesim 2023.1, a new era in modeling smart well completions. Before handing over to our guest speaker today, I would like to give you a short presentation about OBA Energy portfolio and the work that we do in OBA Energy. And also before the presentation, I'd like to have a moment to say that we stand with Palestine and we would like to express our deep sadness for the circumstances that are going on there. We pray for them every single moment. So God bless the Palestinian people in Palestine and Gaza. So everyone, in front of you is our dashboard. We are a team represented in 3 countries, in Egypt, Lebanon, and Norway. We have more than 50 instructors with different experiences in different areas in the oil and gas industry. We have conducted more than 75 free webinars for our audience for knowledge sharing. We have conducted more than 35 live courses, all available. For more than 40 mentorship programs. As you see that we are presented on social media. Here are the numbers. We have more than 20K followers on LinkedIn. As you see in the down right side of my screen, we have almost reached everywhere worldwide. I'm not talking here about the numbers of people that we reached there, but we could manage to reach this area, and our voices are listened there. So our core business is our e-learning system, our website, obacourses.com. I really encourage you all to go visit our website. You'll find many interesting courses, both in technical stuff and non-technical stuff as well. Here is a summary dashboard for our technical courses available on our website. More than 600 learning hours in different 50 courses, and more than 350 subscribers in these courses from different countries, more than 31 countries. These courses are presented by excellent engineers and instructors, more than 60 instructors in different oil and gas aspects like reservoir engineering, production technology, drilling engineering, and so on. Our newly added section for the website is our e-learning non-technical soft skills education, more than 200 courses with 200 learning hours and more than 20,000 subscribers. This is a screenshot from our website, so I really encourage you to visit it. We also have a specialized learning system, e-learning system as well, which is our mentorship program. This is one-to-one learning experience. You choose your instructor, your mentor, and you design your learning journey with OBA Energy. This is some beautiful pictures from our gallery for some of the internship programs that we have conducted here in Egypt for different groups of students from Lebanon. They also enjoyed some geological trips in the areas of Egypt and some interesting visits to major energy companies here in Egypt like Schlumberger and Baker Hughes. Just a quick note for our 10th wave of live courses. We have 4 interesting courses during November, December, and January. If you'd like to apply in any of these, I will let you know the registration link in the chat now. Now you can find it in the chat area. So the dates are colored according to each course, and you can find this also in our LinkedIn page, pinned and available all the time. We also our channel partner for paraffin scale prevention tool here in Egypt. In front of you are some of our clients and success partners inside and outside Egypt, like EGBC, MB, GBC, and Ganob, many clients and success partners. That's it. Before we go ahead to our webinar, some few rules. I'm sorry for muting all your microphones to make it clear for the instructor and the participants to get the knowledge that we are sharing. If you have any question, please put your question in the chat box, and I will read it loud to our guest speaker today, Engineer Ahmed Shammari, to answer your question. Please, if you are joining using a name like Galaxy, iPhone, or something like this, I really encourage you to rename yourself so that we will be able to send you a certificate of participation in this today's webinar. Thank you, and now is the time to introduce our guest speaker for today's webinar titled Pipesim. So our guest speaker for today is Engineer Ahmed Shammari. He is a principal production engineer with more than 20 years of experience in production engineering, flow assurance, and digital oil field solutions. Prior to joining Schlumberger in 2017, Engineer Ahmed worked with Saudi Aramco for more than 15 years. Engineer Ahmed holds a master's degree in petroleum engineering from King Fahd University of Petroleum Engineering. Engineer Ahmed, thank you for joining us. The stage is yours to start the presentation. Thank you.
Thank you very much. Can you hear me? Or not yet?
Yes.
Yeah.
Yes,
okay.
I can see your screen and voice.
Yeah.
Go ahead.
Thank you very much. So it's a pleasure to be with you today. And I totally agree with you that in your introduction that our brothers in Gaza and Palestine are passing through huge, devastating, I would say, tragedy that's happening to them. Fortunately, we cannot help, but we hope that the international community understand what's the situation and try to end the massacre as soon as possible. Now going to Pipesim. So today I'll be sharing with you what we have released last September, which is Pipesim 2023, focusing on smart well completions and flow control valves. And with that, I'm going to describe to you a new concept, a new well type that we have introduced in Pipesim to enable the modeling of smart well completions and many others. Before I go to that specifically, in case you're not very much familiar with Pipesim, let me just give you a quick introduction about Pipesim. Pipesim has oil gas mechanistic flow model, which is the industry standard flow model for modeling multi-phase flow today. Has advanced PVT and fluid modeling capabilities, including link with, of course, integration with multi-flash. We have SLB has a fluid package called Symmetry from our process simulator, which is Symmetry. Pipesim offers detailed heat transfer calculations in pipelines as well as in the wells. We have integrated wells and network model, and I will have a slide talking about that. And there is I would say, misconception about Pipesim from probably the name of Pipesim. It says pipe, it starts with pipe. However, Pipesim is a complete solution for modeling the production system, starting from the sand phase all the way to the gathering manifold, which means that it is very powerful modeling wells with all its granularities, design, optimization, etc. And today's presentation, which is the advanced well editor, talking about modeling of smart well completions, is an extension to what we have done over the years for well modeling. We have a unique feature, which is the integrated GIS pipeline profile, in which you can build the pipeline network automatically from GIS or Geographic Information Systems shapefile, and then you can also visualize the results. I'll also talk about that in a moment. we have what we call the network production optimization and extensibility and automation. Okay. Before I continue, let me just, I know that CO2 right now is a hot topic everywhere. I'd like to emphasize that Pipesim for modeling CO2 transport and injection is very powerful and reliable. And we have recently compared Pipesim with experimental lab data. So CO2 transport modeling in Pipesim is validated against this experimental data and found to provide highly accurate and reliable simulation results. The transition between the liquid and gas phase is handled using pH flash calculation. CO2 transport is carried out using the most reliable flow model in the industry, which is Olga-S. And if you're familiar with Olga, there is an ongoing joint venture project that has been funded by several clients around the world to validate CO2 and to prove CO2 transport modeling in Olga. So whenever this is done, every time we have a new version of Olga-S, we will incorporate it into Pipesim, which means that Pipesim will always get the most accurate flow modeling capabilities from Olga. For PVT modeling, Pipesim incorporates the best equation of state for modeling CO2, including CSMA, GERG, and others. When it comes to the term of integrated wells and network modeling, so we know our competitors. You don't need separate software for modeling the wells and another software for modeling the network. And in my opinion, this is a big advantage because when you have one software for modeling the wells, another software for modeling the network, this could result in making silos between teams. Whereas when you have one model which is integrated, this model can be shared, and if you have a shared environment, you can open the network, update the model within the same network, and then everybody can utilize the latest updated models with all the well data. The simulation, which is more important also, the simulation is solved, or the simulation solves the integrated model starting from the reservoir boundary conditions all the way to the gathering manifold. So you don't need to create lift curves in between to basically account for the pressure drop in the well. So the iteration is happening with all its accuracy from the reservoir all the way to the gathering manifold, including the well, even if the well has artificial lift or any restrictions, so forth. Simple model management and relatively small file size. You can have a model of 500 wells with all its pipelines, and the size is maybe 200 megabyte. And this is, and you can easily navigate from the network perspective to the well perspective by click of a button. There is a button here called perspective here. As you can see, this is W for a well. You just flip it and you go to the network, and then the entire network model with all the wells will be saved in that file. Comprehensive well modeling. So we have several simulation tasks available, including nodal analysis, PT profile, and system analysis. The PT profile is very powerful because you can use it to calculate the required productivity index for a certain rate or the required pressure. It's just one calculation that will give you, and you can perform, of course, sensitivities to see the pressure profile. And of course, the system analysis is the parametric study that you can perform sensitivity analysis. Advanced gas lift and ESP design. You can completely design an ESP system or a gas lift system with all the valves. Of course, there are integrated catalogs, and you can add your own valves or pumps. It considers multi-pointing and throttling for the gas lift valves, and there are various IPR models, including trilinear IPR for unconventional reservoirs. Of course, all the standard IPR models, such as horizontal, Joshi, Babel Node, all the gas IPRs, and of course the productivity index are already there in Pipesim. So for the GIS integration, as you can see from the picture here, you can easily, if you have the network, you can easily, by using the color coding, of the results. For all the results, you can identify issues and identify problems. In case, for example, you'd like to say, okay, where is the lowest velocity ratio to look for corrosion? Where is the highest corrosion rate? Where is the maximum erosion? And where is the, let's say, the highest pressure, etc. So this is, I would say, for large networks is an excellent feature. And of course, you can import a shapefile. For people who are a little bit familiar with GIS, when you go to any GIS system, the map that you see is actually composed of multiple layers, and each layer is a shape file. So, for example, when you go to Google Maps, you can change like, for example, when you look into the 3D map or the actual map, not the topographical map. When you zoom in, you start seeing more data, right? And these data is actually the shape files. So pipelines are also stored using shape files. So for mapping purposes, if you have any GIS team in your company, you can ask them to give you the shape file for the pipelines, and you can just import it to Pipesim and build your pipeline network automatically. And of course, you can digitize on the pipeline path to build the pipeline network, and the network, the length and the pipeline profiles would be also calculated automatically. And then we have finally the network optimization when it comes to the core features, in which it will automatically calculate for you the distribution of gas lift system, for example, gas lift rates per well, the distribution of the ESP frequencies or the choke settings to maximize production and of course honor the constraints. If you have, let's say, some scripting, or you like scripting, you can actually interact with the models without really opening the user interface. So the Python toolkit, you can build and update models using Python scripting without opening the UI. This, of course, helps you to run batch simulations and analyze the results. And it is suitable for all users with basic Python experience. So you don't really need to be very, I would say, a big developer or something. And also we have other extensibility and automation frameworks. We have a cloud native engine service API. This is what we use in what we call Delphi in SLB, which is our cloud answer. And we have a C++ API that enables linking Pipesim with third-party applications such as process simulation. Okay. So now, what are we doing? What's the latest features that we have implemented this year? So the big thing is really the new tab, which is the advanced well, and I will focus on this a little bit. We are also enabling modeling flow control valves along the completions. We have a new GIS map background, and we have enabled the phase ratio override on multi-flash files. So the advanced well. The advanced well is really a new revolutionary concept in modeling wells. I don't believe there is any other competitor that can do this today. The reason is because we are breaking down the well into nodes and branches and utilize the network engine solver. So right now, as you can see here, for example, in this well in the middle here, you have flow that's going into the annulus from the upper completion. There is another one that goes from the lower completion, and then whether the flow goes to the top or to the bottom. As you can see, this is a network, right? But then Pipesim, using the same user interface for wells, will automatically convert this system into a network and use the network engine to solve that, right? So this unlocks huge potential for modeling complex well configurations, such as smart well completions with flow control valve, dual strings, models the flow and tubing and annulus independently, ability to model the ESP separated gas in the annulus, and also it's used for steam circulation. What is the motivation? Why did we do this? Okay, so to deep dive a little bit more on what is actually the advanced well. If you're familiar with Pipesim, this is a well cross section for a well, right? In Pipesim. of course, you can model multi-layer. However, each layer has to be exactly on the same depth of a sleeve. And the sleeve really is not a mechanical sleeve. It's just to open the flow path in front of the completion. In Pipesim, the well canvas traditionally is considered, and it must be a single branch, meaning this is a single branch from bottom up, or for rejection from top to bottom. And as I said, even if I have multi-layer, this multi-layer is not really another flow path. It will add to the same single flow path. The moment, if you're familiar with Pipesim, the moment you move the completion a little bit up or down, or you move the sleeve up or down, Pipesim will give you a warning that I cannot solve this, because then it becomes it becomes basically a commingled flow, right? And in Pipesim, we have two separate engines, right? In fact, so in behind, what you don't see is that there are two completely separate engines for solving the tasks. For the wells, we have what we call the single branch engine, right? And it handles all the tasks related for the well: nodal analysis, PT profile, system analysis. All that is really a single branch engine, right? And you have a completely other engine for solving the network. So the network accepts commingled, of course, branches and etc. The concept, the solver for both is different, right? The numerics are different, right? So now we said, okay, we want now to enable this or these complex scenarios in the well, but the well editor cannot do that, and the well editor itself only talks to the single well or single branch engine. So the well editor is a single branch configuration, does not allow for commingled flow paths, and flow control valves were actually available, but using keywords. It was available Pipesim Classic, but then you can only have the flow control valve as part of the completion. Just it adds pressure drop to the completion. So it's not really an actual flow control valve as we wanted it to be, right? Because the flow control valve by itself can be placed anywhere along the tubing, and you know, the flow can go into the annulus and so on and so forth. So this well editor was limited, okay? And we have, of course, the network editor. So some clients have used the network editor to model smart well completions. Like in this case, for example, we have a well that was developed using the network editor. This is the tubing, and then we have flow control valve here. It's a choke actually, and then we have a lateral here. And said, you know, you can of course don't do that, but it is still the network editor. So it can be used manually to construct some advanced well configurations. However, it's not suitable for all the well configurations. And the problem also is that suppose that you need to model an ESP, or you need to model a gas lift, or you need to model, you know, it's going really to be a hassle, right? So then this is what we have been working on in the past 2 years. It's the new solution. It's the advanced well editor, right? Where the well components are converted into an equivalent network automatically, and the network solver is used to simulate the network system. This opens doors to simulate various advanced well scenarios, such as dual string, steam circulation, as I mentioned before, smart well completion with flow control valves, and modeling of ESP separated gas in the annulus. So for smart well completions, this is released already now. It's released since last September. This is a cross-section for a well with flow control valves, and I will show you a demo today, right? As you can see here, we have a horizontal well, and we have flow control valve here. As you can see here, this horizontal well, Pipesim recognized that there is a flow control valve, which means it breaks down the completion at this point automatically, and then the network that will be constructed basically is going to, you know, create a node here. So there will be the completion will be broken down here, and then the flow will come from the bottom to this node, and then from the top to this node, or from the right and from the left to this node. This is how the network is solved. Then the pressure drop across this flow control valve is calculated. Then there will be a flow stream between the downstream of the flow control valve to the downstream of this valve. And as I said, here also we have the flow coming from this completion to the flow control valve, from the bottom completion to the flow control valve, and so on and so forth. So as you can see here, and then you will notice that we have what we call tailpipe now. This was not available before. So this is just a pipe with a hanger, of course, or with a packer to install to hang over the flow control valves. And of course you can put packers, and then you can go to the rest, right? So flow control valve can be placed along the tubing or a tailpipe as a downhole equipment. Flow in the annulus is modeled. The flow control valve catalog was uploaded with all SLB valves, and with the ability to add custom valves from other manufacturers if you have them. So the supported scenarios, you can use the flow control valve concept for well design with user-defined or catalog equipment. You can use it for production or ejection into separate zones with existing flow control valve settings. You can search for the optimum flow control valve position using the rate limit. So you can put a limit on a maximum liquid rate, maximum gas rate, maximum water rate, or maximum mass rate, and automatically the engine will tell you what is the required position, right? Remember, this is not going to be to find the optimum. It's just you put limit, and then the limit can be on any of the valves, and then automatically the engine will, based on the hydraulics and the inflow coming from each completion, it's going to calculate the required flow opening, or it will calculate the required area or the equivalent area along the flow control valve. So this is just to explain more how we're doing, how we're constructing the network, right? So the same network before is now, I just converted into vertical using the format, right? But you will see that we have this completion at the bottom. We have flow control valve here. These are two single point completions. So this is distributed completion, and these are two single point completions, okay? You will notice that we have actually three streams, okay? So we have flow stream in the upper zone, and this is, from this completion to the flow control valve, from this bottom completion to going up to the control valve, and then across the flow control valve. And we have also this bottom zone, which is a horizontal completion. It is actually split in this location, and then the flow in the annulus is also calculated. And now we have the flow inside the tubing. So this is the annulus, this is the tailpipe, and this is the production tubing. So if you open Pipesim, you will see that you will have these green lines. The green lines represent the flow paths, and this is, of course, as I said, is going to be converted automatically into a network, and it will be solved using the network engine. This is a schematic, or this is just a screenshot of the flow control valve input. So you can have either a generic valve, and then you can enter the equivalent choke area, or you can use a specific valve from the catalog, and then you can specify the opening, right? Depending on the equipment description, of course. This is the limit. You can put the maximum liquid, maximum gas, maximum max, maximum water. And if you have selected the equivalent choke area, this equivalent choke area will be calculated using this maximum. Of course, if the rate is more than this maximum, right? Like, for example, if you say the equivalent choke area is 0.15 inch square, and based on this configuration, the flow across this flow control valve is 1,000 barrels, and then you say the maximum liquid rate is 1,200, it will not calculate the required opening. So it is just backward. So it's just going to restrict. That's why it is maximum, right? So this is just to be clear in this specific scenario. So this is it when it comes to the smart well completions and flow control valve. As I said, I will make a demo, but let me just show you two or three more features that we have added recently. So in 2023, we have added the phase ratio override using multi-flash files, multi-flash PVT files. This was not available before, but some clients requested that, so this is now available. We have also added a new GIS map background, solid colored, right? Some clients said, okay, I know that I like this GIS map. However, sometimes the earth features are making the color coding not very clear. So it's better that I need to switch into a solid color, either gray, light, or white. We have added that. And we have also added easy access to the simulation results file. So some clients who are familiar with Pipesim Classic, that was 2013. If you use Pipesim Classic, once you make a run, it will create a bunch of simulation files. And these files used to be, generated in the same directory that you store the model with, right? So in Pipesim, we don't have that. We have all the results in a comprehensive and powerful, I would say, grid visualization and plot visualization inside the user interface. But some clients said, I am still interested on these classic files. So then if you're also interested, you can go to the results manager, and there is a new button here called Open Simulation Folder. You will find these files. However, these files are temporary. So the moment you close the model, these files will be deleted. So if you want them, you can just copy them and put them in another directory. What is coming soon? So what we're working on right now, this is expected to be released in December. In a couple of months is the dual string configuration. So this is an actual clear. So this is actual and screenshots from our development versions. This is inside my machine right now. We do have dual strings. So you will get in December is that, as you can see here, this long string goes to this completion. This short string goes to the upper completion. We can have gas lift valve ports. We're not yet there to model the entire production gas lift injection valve system. If you're familiar with the injection valve system, is a more sophisticated gas lift modeling capability to model well status, whether it's open, closed, throttling. Here we're modeling gas lift valve ports, in which you specify yourself the injection rate in each valve, and then you can of course play with that manually to match whatever you are producing. Of course, we will continue in next year, Q1. We plan actually to implement the full injection valve system so that it will actually calculate how much you're injecting in each valve by just specifying the casing head pressure at the surface. Dual string configuration enables operators to produce from different zones with major variation in pressure and fluid types. Determine the gas lift split factor between the two strings utilizing the network engine solver. Utilize this configuration for steam circulation in SAGD operations. Of course, without the gas lift valves and without the packer. So in this scenario here, it is used in steam-assisted gravity drainage, in which you inject steam in the long tubing and produce it in the short tubing. Again, for dual string, so you can produce from 2 or 3 separated zones, inject into 2 or 3 separate zones. Of course, the third is basically the annulus, if you want. Circulation, injected long, produced in short, free flow and artificial lift, support ESP in one or both tubings, and gas lift single valve in one or both tubings. With that, I'm done with my presentations. If there are any questions, please put them in the chat. Otherwise, I'll start showing you a demo. Okay. So I'm opening now 2023.1, the official release that was released last September. Okay. Just for the people who are new to Pipesim, I will just quickly go over the will canvas only, right? So this is what you see when you open Pipesim. If I go to, you have network and you have will, I can create a new will, right? So when I click on new will, this will just show you how easy I can build a will model, right? So now you see this is the will head, okay? And I can, as you can see here, for the people who are familiar with Pipesim, in the will canvas, there was only two will types: production and injection. Production and injection. Today we have a new will type which is called advanced. Okay, and let me also let me just go quickly into the conventional will, and then we'll see how the advanced will work. Okay, so I'm going to add a casing just by drag and drop. I'll put a casing here. The casing by default goes to 10,000. So let me just make it, for example, 7,000. Okay, and the inside diameter, I'm just making it. I will just put one casing. Of course, I can put multiple just to represent the what's actual in the field. And this is used if I want to calculate the heat transfer calculation. But let me just put one casing that goes all the way to 7,000 feet, and then with inside diameter of 6 inches. And then I will put a tubing. This tubing goes all the way to, okay. Shall we take questions now?
Yes, no problem.
Okay. So in case of dual string, is it available to do ESP with gas lift in the same string? No, that's not possible. Because I mean, is this even practically possible to have gas lift and ESP in the same well? Mohandes Abdul Qadir. I mean, if there is a need, of course, we will make the effort to do it. However, we thought that this is not really very practical and not very common. Okay, having ESP and gas lift in the same. I mean, there has been trials in the world, but this is not really very common, very practical. The reason is, you know, the ESP requires motor, requires certain power, electricity, and the gas lift requires, of course, you know, to inject in the casing. So, anyways, so you can type in the chat if you feel that this is, you know, there is trail before. I don't know if you're typing correct, but it is available in the conventional. I know in the conventional Pipesim, but not in the advanced will. We elected to focus on the main practical, you know, functionalities. Anyways, let me continue. So we have now. Let me just see if there's another question. Thank you for this presentation. Please, can this Pipesim do cost analysis? If it can, how? Cost analysis. So we have another software for cost, but Pipesim is a hydraulic fluid flow simulator, right? Of course, it can be linked with other products. The network, for example, can be linked with other products, but Pipesim itself, no. Pipesim is a scientific multi-phase flow simulator. Okay. Okay, of ESP, we can use the same gas to produce heavy oil in smart completions. Yeah. In dual completion, how gas lift operate from every tube. So in the gas lift, for dual strings, right? You inject in the casing. So the annulus has the injection gas, the gas lift injection gas, and then each string will have a valve. Okay, So and then the valve will open, then you will inject in each string. This is how it's applied. There is a client in Nigeria right now asking for this. Petronas, for example, has a lot of dual string gas lifts, right? So let me just show you quickly. So this is let's say 3.5. Okay, that goes all the way up to, for example, 6,000. And then I'm gonna put a packer. Okay, then I will add a completion. So the completion here, I'm just going to use productivity index. So I'll specify the completion pressure to be 2,500, 200 degrees temperature, productivity index say 5, and then I'm going to add one fluid, let's say light oil and gas, specify the GOR of 400, and then the API, let's say, is 32. And I'm done with my well. I can now perform analysis. So my well now, as you can see here, the completion is at the depth of, let me just make it a good number, so 6,500. So this is my completion. The completion is described by reservoir pressure 2,500, temperature Fahrenheit in terms of the temperature degree, and, and the productivity index of 5. We have added a fluid. The fluid is no water cut, GOR 400, gas specific gravity, I'll just put 0.8, for example. And then we have 32 API. So this is the fluid. This is my completion. And then we have a tubing. The tubing is at depth of 6,000 with a side diameter of 3.5. And then that's it. This is the flow path. Of course, I can add surface equipment. I can put a flow line, a choke, etc., or I can stop at my wellhead. Let's, for example, add a choke. I'm going to connect the choke with a connector. So the choke now is, let's say, it's fully open. Let's say 3 inches, and then I'm going to add a flow line until it goes to a sink. So the flow line is, for example, is 4 inches, and then the horizontal distance for this pipeline is, let's say, 100 feet or 500 feet, whatever. Now, as you can see here, there is a small, square, which means that right now we have what we call the well stream outlet. So defining the well stream outlet is useful in the network. In the well, I can change that. I can, easily, I can just say right-click here, set as well stream outlet, which means that everything here will be calculated in my simulation. Okay. Now, in my well stream outlet, I can specify the pressure here. Let's say the pressure here is 250 psi. And that's it. So as you can see here, I have a choke, 3 inches. The pressure at the well stream outlet is 250. And now I can run my simulation. So I can go and I say, okay, I need to run what I call a PT prof. Let me just run nodal analysis. This is more I would say, common. So nodal analysis, my node point is at the bottom hole. And now I can simply, as you can see here, the nodal point is at the nodal analysis here. And then the branch ends at the flow line, which is where I specified my well stream outlet. This is the flow line, right? And then I can click on run. Then we have our production. So this will, under these conditions that I specified, is 4,000 plus, right? Whether the reservoir pressure is equal to the bottom hole pressure, if the condition already mature oil field. So there will always be a drawdown between the reservoir pressure and the flowing bottom hole pressure. So the flowing bottom hole pressure is basically, when you start flowing, is the difference between the static reservoir pressure and the flowing, because there will always be a drawdown, and this drawdown is determined by how much PI we have, how much skin, and so on and so forth. You will never have, for a flowing well, you will never have a flowing bottom pressure that equals the reservoir pressure if there is production. There has to be pressure drawdown, right? So this is the nodal analysis. As you can see here, this is my inflow. I have presented several presentations and webinars describing nodal analysis. You can refer to that. So this is the inflow, representing the production from the well, from the completion to the well, and this is the outflow, representing the production from the bottom hole to the surface, including the choke and the flow line. Now, what I can do is I can say, okay, what is the impact of changing the choke settings on my production? So I can go to the outflow sensitivity, because now the choke is part of the outflow. I can click on the choke, and then I can put the bean size. So I can put, let's say, remember our choke was 3 inches, right? So I'm going to put 0.5, and then 1.5, and then 3. So this is sensitivity for the outflow. So when I run, you will see now that the outflow will have 3, see, it will have 3 curves. Each is associated with a choke size. And then this will give you right away the production per case, okay? So as you can see here, this is the bean size of the choke is 0.5, and it gives you 1,300. This is for 1.5, and this is 3, okay? And of course, I can put several nodal analysis, several inflow cases. Like, for example, okay, I will go to the completion, and I can change the productivity index. Let's say my productivity index was 5. So I'll put for example, 1, 5, and 20. Then I'm going to click run. And now you will see that I have 9 cases because I have 3 times 3. So this IPR here, the blue one, is associated with what? With a productivity index of 1. This is with productivity index of 5. This is with productivity index of 20. And now the outflow is associated with the different choke bean size. Okay. So as you can see here, I have 9 cases, and all of them are operating. Okay. Now this is the nodal analysis, and of course, as I mentioned, we have the PT profile. The good thing about PT is that when you run it, it's not nodal, meaning it's not CPU intensive, because I'm not sure if you're familiar with nodal, but nodal requires really more than probably 60 runs, because to construct one IPR curve, you will need to sensitize on the rate and then calculate the bottom pressure for the inflow. And you also need to sensitize on the rates and calculate the bottom pressure for the outflow, then find the intersection. So it is, I would say, a heavy calculation. The PT profile will just iterate on the same condition. Like, for example, when I run, it will immediately give you the, how much we're producing, right? And then I can also sensitize. But then, in addition to the sensitivity, I can, you see the calculated variable here? This is a very powerful tool. So for the calculated variable, we are now calculating the liquid flow rate. Now, I want to calculate the wellhead pressure. On the wellhead, the pressure at the well stream at the end of the flow line. If my rate was not 4,000, if my rate was, for example, 3,000, okay? So I can calculate the outlet pressure, and I will specify the rate. When I click run, this is the pressure, okay? Better than this. If I want to calculate the choke bean size, to give me a certain rate, I can do that directly without needing to do inflow outflow sensitivity and the nodal analysis. Like, for example, I will tell them, okay, give me the choke bean size that will provide 3,000 barrels. Okay, the minimum value is, let's say, 0.5. The maximum value, of course, is 3. And direct meaning as the choke bean size increases, the rate will increase. So now when I click run, it immediately gave me the exact value of the choke bean size. So this choke bean size, if I take it and apply it in the well, I will get exactly 3,000. So let me just do that. So I'm just gonna here say, okay, it's 0.934. So now I'm going to go to my choke, 0.394. So go here, 0.394. And now I'm going to, again, go to PT profile. Now solve for the rate. Solve, the calculated variable is the rate. Everything else is fixed. Remember, I changed now the choke size. No, why is this happening? Okay, let me, before that, originally the choke size was 3. So if I calculate the liquid flow rates, so we have 4,000. Now I need to calculate the choke size. Let's start with 2. Maximum value is 3. Okay, we're ending here, so okay. Unconverged. Okay. Okay, 0.93. Okay. Let me see. If I go to, I need to see what's happening here. Why? So if I go to calculate that, okay, I'll go to sensitivity and as a choke, bean size, and then I say 0.5, 0.934, 2. Yes, what happened? So that's correct, 0.394. Now, if I go to the bean size and I put 0.934. Okay, now I know what happened. I was putting 0.394. So now calculate the liquid flow rate. Should give me 3,000, exactly. Okay, sorry for that hiccup. Now, any question? Oh, thank you. You put it on the chat, on the chat. Thank you very much. So, any question before we start talking about the advanced well? Okay. Now, let me open one of the existing examples. So I will go to help, case studies, and then I'm going to well models. There is an example here called multi-layer, let's say horizontal multi-layer producer, okay? And now I'll try to explain to you the main difference. So right now, you will notice that we can have multiple completions. And I can simply go to the PT profile, I can run it, it will tell me basically how much each completion is producing. I can simply go to the grid. I can look into each of the completions, and I can see how much each completion is producing. So this is the, the production per completion. Okay. Now, what is the limitation for the current conventional well? Okay. The moment the user interface recognizes that there is any commingled flow, it will stop. Let me show you. If I extend my tubing to be up to, for example, so I'm having this this is a distributed completion. Okay. So this distributed completion is between 13,500 and 15,000. So what if my tubing now, I will just put it somewhere here. Like, for example, I'm going to say, okay, it is at 9,000. What do you see here? It complains, right? This is the conventional well. Why it complains? Because go to the validation, it says well is not solvable for multiple completions with converging flow paths. You may need to insert the sliding sleeve at the same measured depth as the completions. So, in simple terms, Pipesim recognized that I don't have a single branch anymore, so I cannot solve this. Okay. Then we said, now we need to solve this issue. So, what if instead of only that tubing, I can extend the tubing to go all the way up to maybe 14,000. And now, not only this, I'm going to put a tubing plug at the end of this tubing. And now I need to open flow control valves. So this is now only available if you, as you can see here, this is not available for the conventional well. You can go to the advanced well. And now I have new equipment. So I can simply go and place my control valve here. And then I can specify the equivalent choke area. So if I'm using a generic valve, I can specify either the equivalent choke area, or I can use the port diameter and number of ports. So if, for example, you have a valve that had the certain ports, you can specify the port diameter and the number of ports, or you can have the equivalent choke area. Like, for example, let me use equivalent choke area of 0.1 inches, for example. Now I have one flow control valve here. I will put another flow control valve there. And as you can see here, look, this is the beauty or the strength of Pipesim. This is a horizontal well, okay? This is a horizontal completion at the top. It recognized that the whole flow coming from this completion must go down, because there is no other way to flow. This completion here in the middle has actually two possibilities. It can go to the upper flow control valve or the lower control valve, and that's why it is split in the middle. It's not actually in the middle, it's in the ratio between the depth. So you will notice now, if I put the format vertical, right, you will see that I have this completion here. It used to be, it's called middle, right? But then you will see that it's called middle 1, middle 2. It is split. And then it is split in one node. It will create a node here. And then the flow across the annulus is going to be calculated, right? Now I found a validation. Let me see what is the validation. So I have two validations. Number one, the geothermal survey. In the advanced well, you have to cover all the equipment. So the maximum must be 15,100. So I'll just put 15,100. I removed one validation. Another validation. Apparently, I did not enter this equivalent for the second one. So the bottom one is 0.1. I'll put the second one is, let's say, yeah, 0.2, for example. I'm going to use a specific valve in a moment. So now, what do we have? We have, this is a horizontal completion. Of course, I'm showing it as a vertical, but I can go again and make it like that. And now, if I go to the home, if you're familiar with Pipesim, we used to have all these tasks, right? But now, since this is not a single branch anymore, it is actually a network, we cannot run these tasks. The engine will not accept it. So we have created a new task. We call it system performance. The system performance, when I click on it, the look and feel is very much similar to the network simulation task. But you will see now that I have multiple completions, and then I have a stream outlet, which is basically at the flow line. Even now, the icon is different. So you will see that the icon now, I have, depending on the open flow paths, I have T that says tubing. If I deactivate this packer to open the flow path in the annulus, you will see that I go to the surface equipment, and I have now two ports. I have one port for the tubing and another port for the annulus. Not only this, look into this description here. I have a tab for the tubing and another tab for the annulus. I can have a different pressure for the annulus, and it is going to be solved. Okay, but let's delay that for the time being. So I'm going to go back to my packer, and I'm going to make it enabled so that I will close the flow path in the annulus. I am here in my system performance. Now I will click run. It's running now the network simulation engine. It's using the network simulation engine. Converged. So let me just try to do one thing. So to describe what we have now, I will just make it 1D. So yeah, 1D, and then I'm going to bring this to the side. So let's analyze the results. What do we have here? This orange graph is what? Is the flow line stream outlet. Is the name of this branch here. Okay. Let me just uncheck it just to focus on the rest of the, completions. These two pressure drops are across the two valves here, the two flow control valves. So this one is this branch, flow control valve at the bottom. This one is the flow control valve at the top. This is the pressure drop. Look, since this is production, so it is starting, the node is here, so then it's going to be from this, the full completion here, from this point all the way up to the flow control valve. So this is going up. So this describes this flow here. Then we have this completion here, which is the middle, okay? Here it is, okay? And we have the complete middle one and middle two. the blue and the brown one. So going up and down. Part will go up, part will go down. This is the pressure drop across this valve. And basically, this is the production coming from this completion. And then I will add this. So this is the you know, and of course, if I want to see the values of the results, I can simply go to the node branch results. So here it tells me how much each completion is contributing. This is the upper completion. This is middle one and middle two, right? This is the flow control valve, okay? This is the current flow, right? And this is the current flow for the, you know, the other valve. So now, let me, and of course I can look into the branches. So each branch, you'll see that here, for example, this branch is backward because the network was saying that, okay, this branch is from the flowing middle two, this is flowing middle two, up to the flow control valve 1. Now it says that it is flipped. That means it's going down. Okay. So now let us just have a look into the other type of the flow control valve. So let's assume instead of using a generic valve, I'm going to use a specific valve. So when I say specific valve, I can now browse for my catalog of the valve. So I can go to, of course, in our software here, we're using SLB valve, but you can add your own. Or Schlumberger in that, the old D. How to isolate between the 3 zones without inflatable packer. I mean, if you want to put a packer, right? I mean, you can easily, let me just add the valve and then get back to you. So I will put a valve, let's say this valve here, okay? And now automatically it is fully open, which is the 7, okay? 7, position number 7, right? So just to answer the question, if you want to add a packer, you can simply drag and drop a packer anywhere. And then it will recognize that. So you can isolate if you want the zones anywhere. Okay. You can put the packer at the bottom here so that, you know, those two are going to the upper flow control valve and this goes to the bottom flow control valve. Okay. So now I have changed this flow control valve. I put it, and you see the position here tells you how much is the opening area. Okay. So let us see now if we do this, how the production will change. So I go again back to my system performance. And remember now that I have changed a little bit the configuration. I put a packer here, so I have isolated the bottom layer to be part of this flow control valve only. So I'm going to run again. So we are converged. Again, I can go to the node branch results. Let me go to the, so this is the flow control valve number 1. So we're producing 9,000 across this valve. Okay. So I need to restrict that. I need now to calculate how much is the opening required so that I do not produce more than, say, 5,000 only. So I'll go to this valve, which is number 1. Let me close this one. This valve is still selected. And I'm going to put the maximum flow rate of 5,000. And then I would like to know what is the required opening that will be associated with this. So click on system performance again, run this again. And now I go to the node branch results. I go to the valve. We are less than 5,000. the position is 4. Okay. So you go and apply this in the field. Another scenario, suppose that I have this completion here. I go to the fluid model, and then I have high water cut coming from this completion. Or to be more realistic, let's go to the bottom completion and we have high water cut. Let's say, for example, the water cut here is 30%. Okay. Now, when I run, just make sure that it was, yeah. Okay. So when I run, of course, this will affect my production. And I will go to my node branch results. And then I'm seeing that across the bottom flow control valve, how much am I producing in terms of water? I'm producing 544 barrels of water. Okay. So this was significantly reduced now. So now I would like, if I want, and let me see how much I'm producing at the surface. I'm producing at the surface, you know, oil is 5,800. Okay. So now I want to restrict, I want to the bottom valve, the bottom completion, not to produce this amount of water. So I'm going to go to this flow control valve, which is now allowing 544 of water. I will go now there and I will tell him, no, I want you to allow only 300 barrels of water. Okay. Now it is going to now calculate for me a new equivalent choke area. So now I click system performance again, run. Now imagine we're having now a challenging case because now we're putting two restrictions on the two valves. So each valve has its own restriction. Now I go to my node branch results, okay? And I see now that I would go to the bottom one, sorry. So now it has 300 exactly because I am now not calculating an open, a step. I'm calculating an exact opening area, okay? So now I managed to restrict this upper flow control valve not to allow more than 300 barrels per day. And of course, the scenarios can be different. Let me just show you different scenarios, different cases. Like for example, open here. Just a second, please. Go to my folder. So look into this case. This is a horizontal well where we are forcing the flow to go to the bottom, and then it goes through this tailpipe. Then we have an ESP. This ESP has a gas separator that is separating 100% of the gas. But where does the gas go? It goes into the annulus, right? Now, if I go to the surface equipment, I will see that the tubing head pressure we don't have surface equipment. So we have tubing head pressure of 400 psi. The annulus is 1,500. Okay. Now, when I run my system performance, I'm going now to model. You will see now what is happening. Let me just explain to you this beautiful graph here. So let me just make it like that. So what do we have here? This is the pressure drop across this completion here. This is the highest. We consider that this is the highest pressure, right? So this is the pressure drop across the completion. Then this is the pressure drop in the annulus until it goes to the tailpipe. Then this is the tailpipe bottom, the green one, the tailpipe bottom to the tailpipe top. Then we have the orange line, which is from the tailpipe top to the tubing bottom. Then we have reached the tubing. The tubing includes an ESP. So there is a jump in the pressure. Then this is the flowing going inside the tubing. The wellhead pressure is 400. This is the pressure drop in the annulus. Now, it is important to mention that the separated gas, in the network solver, the separator always creates discontinuity in the production, meaning this stream is calculated backwards. Meaning because what happens is that the separated gas will be simply injected into that branch, which is the annulus, and then we cannot specify the pressure and the rate in the inlet, so we specify the rate in the inlet and the pressure at the outlet. So now it back calculates, meaning if I change that pressure to be, for example, 1,200, it will solve, but you will see that it is discontinuous, meaning the pressure across C, it's just calculated. So this is one of the limitations on the modeling the separator, because basically the problem with the separator is that it is one node, but then two streams are coming out of it, right? So we cannot put the same pressure on this node, okay? That's why the way we do it is that we solve it backwards for the separated branch only. But then we have, using manual iteration, we figured out that, yeah, the best pressure to represent the annulus at the end of the annulus is 1,500. And we did that before, so that it actually represents the pressure at the inlet of the ESP, because the separator, as you know, must be before the ESP. Okay. And of course, if I go to the grid, I can visualize, I can see the numbers. So I can look into each of the branches. So this is the annulus stream outlet. So this represents the gas, the separated gas. This represents the production in the tailpipe. This is the branch of the tailpipe top to tailpipe bottom, and so on and so forth. So these are the different branches. And of course, you can go to the nodes, and then you can see the completion, the ESP, all the results, and so on and so forth. Tubing and annulus. I think I have been speaking too much. We're more than 1 hour. I've been talking for more than 1 hour, 15 minutes. Didn't feel the time. So let us see if we have any more question. Okay. I was about to ask this question, but you already mentioned the sizing. In case if you have layers of different rock and fluid properties, as well as pressure, how to ensure having the same PWF for the sake of avoiding having their zone, thief zone while producing. Well, that needs to be done iteratively. So you have to solve it, and then you have to there is no restriction on specifying the pressure. Let's put it this way. It's only the rate. So, but then you need to solve and analyze and see, because it happens that the production will go, and then the network will show you that the flow will go from one zone to another, and this is one of the also the strength of using the network solver to do that. So, guys, that's it. I'm done. We can open the floor for any more questions.
Thank you so much, Engineer Ahmed, for this informative, I'm not gonna say session, it's a workshop. Really thanks for this time. Guys, I will put in the chat area feedback link for this webinar. So please take a moment to fill in this feedback link. This will help us to improve in the next webinars. Engineer Ahmed, thanks again, and we still have time if you have any questions. Also a reminder that this webinar has been live streamed on our YouTube channel, so don't worry if you missed any part of it. You can revisit it on our YouTube channel at any time. Also, this is the 75th webinar. All the 74 webinars before that webinar are also available on our YouTube channel. So you can revisit any of these webinars at any time.
Thank you, Abdul. Okay, flow control valve similar with inflow control valve. Yes. Yeah, the tool is equipment for the function of water cup. It is suitable to basically the flow control valve or the inflow control valve. Okay, I need to distinguish between flow control device or inflow control. So ICD is different from flow control valve. Flow control valve is similar to ICV, not ICD, because the ICD, the inflow control device, is pre-designed and you cannot change the valve position. Whereas the ICV or the inflow control valve or the flow control valve, you can control the opening from the surface. You can control it's like a choke, right? So you can release it, open it, etc. So you can use it to, for example, reduce the water production for a certain zone and so on and so forth. So yeah, it's and of course for the case of multilaterals, you can also use flow control valves to control production from each lateral. Sure. Okay, I guess that's it. Thank you very much. Thank you for OPA for arranging this webinar, giving me the opportunity. Thank you all the audience. And guys, let's connect on LinkedIn. You can search Ahmed Shammari, you'll find me right away, hopefully. Or let me share my LinkedIn profile here. That's better even. Here is my LinkedIn profile. I put it on the chat. So let's connect. If you have questions, let me know.
Thank you again, Engineer Ahmed. It's a pleasure to have you today. I'm
you.
looking for more cooperation. Thanks a lot.
Thanks a lot. Have a good day. Bye.
Bye.